Thank you, and it's a tremendous pleasure to be here. And it's also tremendously inspirational to me to hear of the awards yesterday addressing great scientific questions. Because to me, the state of science can best be judged not by the questions we've learned to answer, but rather by the new questions we've learned to ask. And so much of today's talk, I want to focus on some unanswered questions relating to carbon. Well, I want to do 5 things. First, I'm just going to briefly introduce a new program, a scientific program that some of you may want to become involved in called the Deep Carbon Observatory. But then I want to address 4 questions. The first being, what happens to carbon minerals at extreme pressures and temperatures of Earth's lower mantle? Then thinking about the idea of organic synthesis in the rather unconventional environment of the Earth's upper mantle. Then thinking about deep microbial life in Earth's crust. And finally, thinking about another aspect of extremes, that's deep time, and how Earth, and specifically carbon mineralogy, has changed through deep time. Now, you'll notice in each of these cases, extreme and deep are relative terms. It depends on the molecular system that you're trying to study. And I think that's true, and we've seen this throughout this fascinating symposium, many different aspects of extreme, and it's always relative to the context that you're talking about. Okay, let me just tell you briefly about the Deep Carbon Observatory. It's a program that was started in 2009 in order to study various fundamental aspects of carbon. We're now into the 4th year of a 10-year program. We have approximately 1,000 researchers around the world in 40 countries, roughly $100 million in funding so far. And this is largely initiated by the Alfred P. Sloan Foundation, an opportunity to study various aspects of carbon. As we've seen, carbon is an extremely important element. After hydrogen and helium, it's the second most abundant element, and indeed about 1 in every 4 atom that's not hydrogen or helium is carbon, only oxygen being more abundant in the terrestrial planets. And so we think about the carbon and its importance. Of course, we only need to look around us to think about how important carbon is. Carbon is the element that's most frequently cited in terms of our energy requirements, our energy use, and therefore, by extension, it's the element that's most of concern in terms of climate and environment. But it's also the element of materials. Look around this room, and virtually everything you see is a carbon-based compound. The wood in the floors, the various draperies, the plastics, the paint on the wall, the ceiling tiles, almost everything you see is a carbon-based material. And this is fundamentally important to our technology, to our well-being. Carbon is the element of life, and of course, by extension, the element of health, pharmaceuticals, and various other sorts of the foods that keep us and sustain us. Carbon is fundamentally important, and we talk about the carbon cycle, but the kind of illustration you find in textbooks almost always looks at the surface, with maybe a slight hint with the oil well in the coal mine that there's something beneath the surface. But what we're interested in is the carbon cycle of our entire planet, and indeed, by extension, other planets and moons. We talk about the various levels of planets, the thin outer crust, perhaps a few up to 10 kilometers thick in the ocean areas, and the continents perhaps several tens of kilometers. And then the mantle, most of the volume of Earth, comprised primarily of magnesium silicates, the core, the liquid metal outer core, the solid inner core. These are the parts of Earth that are really hidden from view and yet may play a very important role in understanding carbon. So the Deep Carbon Observatory has a variety of questions, and we basically organize ourselves around questions. 4 main questions that we address have to do first with just the properties of carbon at extreme conditions of pressure and temperature. Also, the reservoirs and fluxes. Where is the carbon? How is it distributed? And how does it move through those various reservoirs, particularly from the deep interior and exchanging with the surface? Then is there a question about the organic molecules? And of great concern, are there deep sources of organic molecules, non-traditional sources that might influence the surface, might play a role in the origin of life? And finally, the role of deep life itself, an absolutely fascinating topic that's only now coming into blossom, the idea that there's a deep biosphere hidden from our view, but incredibly extensive and truly fascinating. Now, much of this work has been described in a book that's just published, came out 2 months ago. It's open access. So you can just go to the internet, you can download any chapter, and I'm astonished to tell you that in the 2 months since this book came out, we have had 500,000 downloads of chapters already. That's astonishing. This is the power of open access publishing. I just want to emphasize the point that when you make something available free to the public worldwide, it has a much greater impact, I think, than it will otherwise. So I encourage you, if you're interested in any aspect of this and much, much more that I can't discuss, please just Google Carbon and Earth. You'll find this book available free on the internet. Okay, so just to give you a sense of how much we don't know about carbon, the question of how much carbon is in our planet is fundamental. If you take all the known sources and add them together, it's about 0.07 weight% of Earth. If you think about all the potential sources that people have proposed, you might be able to get up to 1.5 weight%. That's with some fairly optimistic extensions. But if you look at the material from which Earth was composed, and those are meteorites called the carbonaceous chondrites, they have over 3% carbon. And so here fundamental questions arise almost immediately. Why, if the meteorite is 3 weight% by carbon, can Earth be so much less? And are we missing something? Is there some deep reservoir in the deep interior? Well, that's one thing we can think about. Think about the reservoirs of Earth, and one way is to look at those shells, and we can say the atmosphere now has close to 400 parts per million. The oceans, the crust, and also the continental crust, where the terrestrial biosphere concentrates carbon in new ways. These are numbers that are very well known, but the huge volume of Earth, of the mantle and the core, absolutely unknown how much carbon. And if there's only a few parts per million or a few tens of parts per million, these would increase by more than an order of magnitude the total amount of carbon in Earth. We simply do not know. And that's one of the things that's discussed in the book and that we're trying to understand. So here's another way of thinking about carbon. Please don't try to read this table. But what this shows is in the vertical scale, all the different potential reservoirs of carbon deep within Earth. And the state of our ignorance is reflected by the question marks, how much we know. So this is something we're trying to come to grips with. What I want to do today is just look at 3 subsets of these different possible reservoirs and see how different and how fascinating they are and the kinds of questions we have yet to answer. So let's first think about deep mineralogy. What happens to carbon minerals at the extreme pressures of the lower mantle? And by this extreme, I mean temperatures above 1,000 degrees Celsius, pressures that can approach several 100,000 to over 1 million times atmospheric pressure. And we know for 100 years some of the story. And that has to do with the element carbon and its allotropes, particularly graphite, which occurs at the lower pressure, and diamond that occurs at higher pressure. And we understand quite well some of the crystal chemical arguments for why this would be. Graphite, beautiful structure, a layered structure in which each carbon is surrounded by 3 neighbors in a plane. When you go to higher pressure, you have to have a more efficient packing. And that's why in diamond, you now see a structure in which each carbon is surrounded by 4. This is a very common phenomenon in high-pressure transitions, going to higher coordination numbers. And so we'd anticipate similar sorts of changes might occur in CO2 and in carbonate minerals and other sorts of things. But the experiments had never been done until very, very recently. And so members of the Deep Carbon Observatory and other scientists around the world have been studying, for example, CO2. This is a structure which you may have experienced in the form of dry ice, solid CO2. And this structure is stable up to about 100,000 atmospheres. But when you go to higher pressures, again, the demand to decrease volume requires new efficient packing, and suddenly you see these single CO2 molecules starting to polymerize into a framework structure in which each carbon is surrounded by 4 oxygen atoms. So we're going from coordination of 2 to coordination of 4 in a very beautiful structure. As you go to even higher pressure, there are now hints coming out of laboratory work that Russ Hemley and others have been doing, looking at CO2 at extreme pressures and temperatures, and you may actually have a hint that CO2 is breaking down to elemental carbon plus oxygen, a fascinating possibility for the lower mantle. And yet a new area this is absolutely only the last couple of years that this is being explored, and new results are coming out, it seems, almost every month. But what happens to the most abundant carbon-bearing minerals of Earth's surface? And those are the carbonates. Limestone, dolomite, formed of minerals like calcite, dolomite, magnesite. These are minerals that are extremely abundant. In fact, they're the principal reservoirs of carbon on Earth that are known today. There's more carbon in calcite and its related minerals than any other form. And the key structural element here is the carbon surrounded by a planar triangle of 3 oxygens. But you'd anticipate if you go to very high pressure, and by this I mean close to a megabar, 1 million atmospheres, you start seeing new denser forms. And indeed, that's what's found. New dense carbonates that are only just now being revealed. This is magnesium carbonate, here's calcium carbonate at extremely high pressure. And what you notice is the carbon surrounded now by 4 oxygens in a tetrahedral arrangement. Well, those of you who have studied mineralogy may see something very familiar here. These look very much like silicate minerals, where you have SiO4 groups at room conditions. We've heard a lot of discussion about carbon versus silicon in the origin of life. Well, silicon has far fewer structural configurations it can take, and they have very specific lower energies. But here's an intriguing thing. Are carbonates in the lower mantle essentially analogous to silicates? And at first blush, we thought this must be true. This looks like what is in mineralogy called a pyroxene-like structure with chains of polymerized tetrahedra. But there is a fundamental difference, and this is a fascinating discovery that's only just coming to light. If you do calculations of the angle carbon, oxygen, carbon, because when you start linking tetrahedra together, there has to be this bridge, this angle. In silicates, which are shown in red here, the energy that's involved in that angle is very insensitive. So you can bend that bond a great deal and not see a lot of energy difference. Therefore, silicates are incredibly flexible structures in that sense. You can adapt them, you can squeeze them, you can twist and contort them in lots of interesting ways. And that leads to the diversity of silicate structures at or near Earth's surface. Carbonates, though, at these extreme conditions, the carbon-oxygen-carbon bond shows very deep wells with a minimum at about 123 degrees. And what that means is that the carbonate structures are constrained to have very rigid angles. And this geometrically causes huge problems. You can't adapt in the same way silicon has. So it turns out that carbon is much more flexible in its kinds of organic chemistry at crustal conditions. But in the lower mantle, silicon is much more adaptable, and it's the carbon that is very inflexible. This is going to lead to some fascinating new structures that are just being discovered. Some of those structures may be super hard because they just don't bend. They're going to be very stiff. It may lead to new kinds of materials, new electronic properties, and some of these structures may be able to be synthesized at high pressure, quenched, returned to room conditions, and therefore provide a whole new class of carbon-based materials that we've never seen before. Fascinating, just discoveries being made now, and so stay tuned. Our second question has to do with the extent of deep organic synthesis, perhaps in the upper mantle of Earth. Now, this is almost heresy. If you think about organic chemistry, you certainly don't think of temperatures of 1,000 degrees and pressures of 100,000 atmospheres. And yet, it's possible. Now, let's look at a controversy that's been around for a number of decades. First, the view of U.S. oil companies and many of the petroleum geologists around the world is virtually all organic molecules that one finds at or near Earth's surface comes from biology. The burial of dead organic matter, the processing in Earth's crust through temperature and pressure. This is what produces petroleum. Natural gas is a byproduct, coal, of course. So all of the fossil fuels we talk about are truly fossils of living beings. But that's not the only point of view that's out there. In Russia and Ukraine, there's been another point of view that, in fact, there's a deep origin of hydrocarbons, that in fact methane and other hydrocarbons form very, very deep because they're buoyant, they find cracks and fissures, they work their way to the surface, and because there is a deep biosphere that processes these hydrocarbons, which are essentially food, then you see the biological overprint in petroleum. This idea was first proposed well more than a century ago by Dmitry Mendeleev, the same individual individual who proposed the periodic table. And this has been very much a part of Russian geology tradition, Ukrainian geology tradition for more than a century. There's also been a resurgence of this idea through a popular writings of Thomas Gold. He's now deceased, but when he first came up with these ideas of the deep hot biosphere, he promoted this idea. And there's this tension. Indeed, one of the things the Deep Carbon Observatory is trying to do is resolve what seems to be a dichotomy, and yet I think it's more likely that many of the great controversies in the history of science have been extremes where the truth is somewhere in the middle. And so let's think about this process. One can have biogenic methane, for example, coming directly by microbial activities with methanogenesis at low temperature. Also the processing of biological material, so thermogenically producing methane. There's also the possibility of abiotic synthesis in the crust or mantle. So we have to think about these ideas and keep an open mind. And indeed, we know for a fact that there are abiotic processes that lead to organic molecules. After all, the origin of life, there had to be organic molecules before there was life, and we see many different ways of making them. But here's a piece of evidence that maybe you haven't seen and find it absolutely fascinating. This is a cross-section of a Martian meteorite. And there are large crystals in this of pyroxene that have little black specks. Now, a pyroxene crystal like this, because it's fairly large, means it formed fairly deep within the Martian crust, maybe several kilometers down. And it was hot. It was more than 1,000 Celsius. And yet these little black specks, if you examine them in detail, they're carbon-rich, and using confocal Raman microspectroscopy, this is work of Andrew Steele at the Carnegie Institution, they're kerogen, they're hydrocarbons, organic molecules produced in mantle conditions on Mars, and certainly the same kinds of chemistry occurs on Earth. And we can demonstrate this in the laboratory as well. Here's work by Henry Scott, Russ Hemley, and others from several years ago, work that's been followed up in many, many laboratories around the world now, showing directly the production of methane from rocks. Look at this, calcium carbonate. That's the same mineral calcite I showed you before, iron oxide in water. That doesn't look anything like an organic molecule. But you subject this to high temperature and high pressure, and inevitably you produce methane, calcium oxide, and then a more oxidized form of iron. And what's going on here is a redox couple. The iron oxide is becoming more oxidized, the carbon is being reduced. And you can see methane bubbles, you can do Raman spectra of those methane bubbles, you can actually look at the iron oxides and see a change in the iron oxide. And so this is a fully understood process. This is an inevitable process in certain parts of Earth's upper mantle, perhaps the lower crust. We don't know how extensive this is. We don't know whether this is a major contributor to the natural gas reserves we see at or near Earth's surface in some places, or maybe just a very minor component, but it surely is happening. And of course, this then leads to another entire talk, or several talks. We can have a whole symposium on the origin of life and whether deep organic synthesis played a role, along with the molecules coming from deep space, as we heard yesterday, and the Miller-Urey type processes, and many other processes. This is an inevitable part of an Earth-like planet. All right, question number 3. The nature and extent of the deep microbial biosphere. An astonishing set of discoveries from the last 20 or 30 years about a truly hidden biosphere, and yet one that the more we look, the more extensive and the more diverse it is. So, studies in deep mines where you can recover fluids up to more than a mile underground, drilling in continental areas, drilling in marine setting, have shown that there's microbes almost anywhere you go. Right here in Stockholm, we could drill a hole down 3, 4, 5 kilometers. We could take up those cores of rock, and if you look carefully at those cores of rocks, inevitably they will contain microbial life. Life that's living far from sunlight. These are life that's living on rocks, and I'm sure in the next talk we're going to hear about these chemo-litho-autotrophs. Chemo means chemistry. Litho is rocks, so you're taking the chemical energy of rock, and that's what you're using as your food source. It's those oxidation reduction reactions because the rocks themselves are not at equilibrium with the fluid that's circulating through them. And therefore, the microbes simply act, if you will, as catalysts, speeding up the weathering, the alteration reactions that would have occurred anyway, and yet they're taking advantage of that chemical disequilibrium to propagate themselves. And throughout the deep subsurface, everywhere we look, we find microbes. Now, How much are there, and what are their extremes? It turns out that the extreme temperature seems to be about 130 Celsius. That's as you go down, increasing in pressure and in temperature, so this is not boiling water. This is simply water that's pressurized and therefore can sustain those temperatures. But no one's yet identified any living microbes. Now, I will come back to this point. There are hints, just hints at this point, of some kind of very complex molecular self-organization, maybe life, maybe something that's, I don't know, at temperatures even above 200 Celsius. This is one of the frontier exciting areas. But we do know that there's an extensive biomass down there. You can do various calculations. In our book here, we've predicted that it may be 15 to 20% of Earth's biomass. There are other estimates out there that even exceed 30% of Earth's biomass. Whatever, it's a huge amount of hidden life. Now, at any 1 cubic centimeter, it's very sparse. But the fact is, the volume of Earth's shallow crust is immense. And when you integrate 10 to the 6th or 10 to the 7th microbes per cubic centimeter over the whole crust, it becomes truly astronomical numbers. So we ask questions about these. What's the nature and extent? How do they survive? Well, of course, there are many ways to do this. One of the exciting new directions is to study the microbes in situ in drill holes. So we're partnering with Katrina Edwards and the CW effort at USC to look down in boreholes and actually do fluorescence spectroscopy, looking at the walls of drill cores and then seeing in situ the effects of microbes. And these instruments have now been deployed, and this is ushering an entirely new era of in situ deep microbiology, truly an amazing frontier. And also, of course, there's laboratory experiments. This is work that a number of us, Russ Hemley and George Cody and Anurag Sharma and myself did almost a decade ago, and many people have followed up, including our laboratories, followed up on this. But this is an incredibly cool experiment. A diamond anvil cell that Russ showed you yesterday is creating high pressures by squeezing a small chamber filled with fluid. In this case, we put fluid with 2 of the commonest surface microbes, E. coli, Shigella, and they just look like microbial cultures when you have them at room pressure. Well, when Anurag was doing these experiments, he got a little overzealous. You have to turn a screw to get the high pressures, and we were all thinking we should just go to 1,000 or maybe 2,000 atmospheres, because surely above those pressures, microbes would, they would perish. But Anurag turned the screw a little bit too hard, and we went from 0 to 14,000 atmospheres. It seemed like a mistake, but because when you first look through the cell, right at the beginning of the experiment, at 10,000 atmospheres, ice forms, ice 10. It crystallizes. It's a different form of ice, but you see these nice triple junctions where the ice crystals have come together. I mean, where are the microbes? There's just nothing. You don't see them. You don't see any fluid. You don't see anything. But you wait for a few hours. And if there are microbes present, and only if there are microbes present, you start seeing little pockets at the triple junctions start to diffuse and become like little bubble-like areas, and there's fluid there, and the microbes are in the fluid. I don't know how the microbes do this, whether this is being studied. And then you lower the pressure back down. Now, they don't reproduce at these conditions. They don't metabolize, but they hunker down, they survive. When you go back to room pressure, some of those microbes are still alive. And you can actually, at several thousand atmospheres, you can use various probes. You can use Raman spectroscopy to probe food molecules that are in the solution. You can see metabolism going on. You can see well-known physiological changes to E. coli at pressure, and then they revert after a time. There's interesting gene expression going on here. There's all sorts of physiological aspects of this that we simply do not understand. But suffice it to say that we now see 14,000 atmosphere survivability of surface microbes, and subsequent experiments have shown that these microbes, some of them can survive above 20,000 atmospheres. So what this means in terms of Earth's surface is that pressure is absolutely not a factor in microbial survivability, because there is no place on Earth where you have a pressure as high as 20,000 atmospheres and the temperature is lower than 130. Indeed, the deepest place where you have cool temperatures is very rapidly subducting plates, the most rapidly subducting area. And one can imagine getting down to about 20 kilometers where the pressure is only 6,000 or 7,000 atmospheres. And that would be maybe the deepest life of cellular form that we can think about on Earth today. There's something else, though. And this is not my work, and this is highly speculative, and just as young people, keep an open mind about what is possible. Let's go back to the origin of life. The origin of life was a molecular event. It was a molecular self-assembly of some sort, and then layers of complexity. Once you had the first self-replicating set of molecules, then you could layer complexity on top of that. And what we see, the modern protein, DNA, RNA type chemistry is much, much more complex than what I think of as the first self-replicating molecular system. Indeed, that first self-replicating molecular system could have been a layered-like arrangement of molecules that self-templated itself and used the chemical energy of rock surfaces, in which case they would have sort of just migrated. Maybe if you had a split or fluids flowing through, you get little fragments of what was like a biofilm moving from one place to another. And these kinds of chemistry could easily take place above 130 Celsius, which means that they've never been eaten. And there have been continuous volumes of Earth's crust for more than 4 billion years, which have been at above 150 Celsius. So if such a self-organized molecular system got started 4+ billion years ago and was a step to the origin of life, some remnants of those self-organized systems must still be deep within Earth. But how would we know? When we look for life, we look for DNA, we look for proteins. And this kind of surface electrolytic gel might have something else. Well, but there are hints now that such complex chemical organized systems are present in experiments at the Wanda Fuca Ridge, which have been reported by Deborah Kelly. John Barros has been involved in that. Also at experiments in deep drill holes in China, in the Songliao Basin. Temperatures above 150 Celsius, where there clearly is some kind of organized molecular structure going on. I don't know what it is. Is it life? Is it life? Is it something else? But if this is true, and if you could survive above 200 Celsius, you could imagine having some kind of organized molecular life at 100 kilometers deep in Earth. So this is an astonishing frontier area, something we don't know, but it's the kind of thing that may make the future of the Deep Carbon Observatory and beyond quite exciting. And finally, my last question, and this is my own personal passion, it's thinking about the nature of minerals through deep time. Because when we talk about extremes, billions of years of history is certainly one kind of extreme. And the take-home message is that there was a time when there were no minerals, then there was the first mineral, now we have lots of minerals, and we see changing mineralogy through time, and this gives us a direct window on both the carbon cycle and the origin and evolution of life through time. This whole area has been called mineral evolution. It looks at the diversity of minerals, just how many different mineral species there are. By the way, a mineral is defined as a crystalline compound, so it has a specific crystal structure and a particular range of chemical compositions. So diamond is a particular crystal structure made of carbon. Quartz is a particular crystal structure made predominantly of silicon dioxide, and so forth. And there are about 5,000 or so minerals that are known today. So the diversity of minerals, the relative abundance of those minerals, their compositional ranges, because virtually all minerals can take impurities, and the nature of the trace and minor element impurities changes fundamentally through Earth history. And also the grain sizes and shapes, something that you see that are obvious when you go to a museum, but virtually no mineralogist talks about. Isn't that strange? The beautiful crystal forms, where did they come from? Why are there different forms for different crystals? We think about these things. Okay, so key ideas. Minerals have always been the principal repositories of carbon on Earth. This is the main place you need to go if you're looking for carbon. But that mineralogy has changed radically through Earth history. And this then reflects changes in the coevolution of the geosphere and the biosphere. Questions. Scientific questions. It's so important to ask new questions, to think about new questions. A colleague of mine, Harold Morowitz, 6 years ago, we were sitting at a party together and drinking a glass of Cabernet. And he just suddenly changed the subject and said, "By the way, Bob, were there any clay minerals in the Archean?" And his question hit me like a ton of bricks, because no one had ever asked that kind of question before, ever. A mineralogist had never asked, was there such and such a mineral at such and such a time? Now, that's strange, but mineralogy has been strangely divorced from geology. Mineralogists, Carl Linnaeus had a system of classification which he talked about plants, animals, and minerals. And he had a binomial nomenclature for plants, animals, and minerals, and he even had genders, male and female plants, animals, and minerals. There are male minerals and female minerals. The minerals were thought of as objects. They had crystal structures, they had compositions, they had properties, but always somehow isolated. You go to a mineral museum, there are rows of minerals, they're beautiful specimens, but there's nothing about their age, their stories, where they came from, their context, how life played a role in their formation. This was not part of mineralogy, and Harold Morowitz asked that question. And then I began to think of new questions. For example, what was the first mineral in the cosmos? It's astonishing to me. No one had ever asked that question before. It's just beyond belief that in centuries of thinking about minerals, no one had ever said, what was the first crystal in the cosmos that had a well-defined chemical composition? And think about it. What was the first mineral in the cosmos? Let's think ourselves back to the Big Bang. At the Big Bang, there were no elements, so no minerals. It's much too hot. And then after a few 100,000 years, you formed the first atoms of hydrogen and helium, maybe a little bit of lithium, but hydrogen and helium don't form crystals, at least not at the kinds of conditions that were present then. No minerals. So you had to form the first stars. And there are no minerals in the first stars because of its plasma. It's much too hot again. So when do you have temperatures cool enough to form a crystal? But the concentration of mineral-forming elements, not hydrogen and helium, high enough that you get the atoms interacting to form a crystal. The answer turns out to be diamond. It's diamond because carbon is a very abundant element in stars that forms one of the outer elements. As a star explodes, the star has regions that are carbon-rich. And diamond is the highest temperature condensing crystal. It forms at about 4,000 Celsius. And you had to cool down another 400 degrees for the second mineral, that was graphite. And then cool down a little bit more for the third mineral, which was moissanite, which is silicon carbide. And here we see the first three minerals in the cosmos are carbon minerals. And this carbon mineral is partly because of the high temperature formation and partly because of the abundance of those elements. And then all the other minerals, the dozen or so minerals that occur and are still preserved in pre-solar grains, they form in these exploding stars in the envelopes of supernovas and other types of energetic stars, AGB type stars if you're interested. And the envelopes of fusion as you go farther and farther out. There's that carbon-rich zone, oxygen and carbon, nitrogen, and so forth. So you get these dozen or so minerals. They're still preserved in pre-solar grains. You can identify them by their extreme isotope anomalies. That's the starting point of mineral evolution. And perhaps the fact that carbon is rich amongst them and the diamond is first, I just love that. But here's the basic question of mineral evolution. How do you go from a dozen to the greater than almost 5,000 today, 4,700 or so? And what does this tell us about Earth history, about the origin and evolution of life? Turns out there's an incredible story hidden in the minerals. Let me take you through that story. By the way, just to give you a sense, we'll use carbon minerals as kind of a foundation. There are about 387 known carbon minerals, carbon forms of diamond and graphite primarily, then carbides, and most abundantly carbonates. These are minerals with CO3 groups, central carbon and a triangle of oxygen around them, and then a bunch of organic minerals that pop up fairly recently in Earth history. Let's look at these through history. By the way, the reason carbon is so fascinating and the reason we've written an entire book and that we should study this more is it is the most chemically diverse of all the elements. It's special, it's unique. You could argue it's the most important element in our lives too, but it has oxidation states from -4 to +4. It bonds to almost 80 different elements in the periodic table. That's astonishing. Carbon actually literally bonds to all those other elements. And it occurs in 2, 3, and 4 coordination in various minerals. So it has these different flexibilities that allow it to do many, many different chemical things. Okay, imagine now you have clouds of dust and gas. the ones that were described yesterday so beautifully with all those organic molecules. And these clouds of dust and gas contain those dozen minerals. Some perturbation, perhaps a supernova explosion, causes a shock wave, and some volume of that cloud and dust and gas begins to collapse, begins to swirl, begins to come together. That's the solar nebula. And 99.9% of the mass comes together in the central sun that's just beginning, our protostar, while all the rest of the debris, what would become the planets and the moons and all the other materials, that's that 0.1% that's on the outside. And at some point, pressure, temperature build. The star begins to go through transitions, magnetic transitions, which cause pulses of energy, what's called the T Tauri phase of the early solar system, the solar nebula. These pulses of heat blast out, and those the dust which has come together like little dust bunnies that have electrostatically stuck together. So now you can imagine dust bunnies in space hit by blasts of thermal radiation. They melt, they condense down into tiny droplets called chondrules. And the first earliest materials of the solar system, you can hold these in your hand, the commonest meteorites, the chondrite meteorites, which have these little droplets. Again, formed at high temperature, but not quite so high temperature. The minerals are all above 1900 degrees or so. These are minerals that are above perhaps 11 or 1200 degrees. And so we have 60 mineral species in all, and this is the earliest building blocks of the planets and moons. Now, these begin to clump together through gravity, larger and larger, a kilometer, 10, 50, 100. When you get to 100 kilometers, this object, because of the gravitational potential and the radioactive short-lived elements produce huge amounts of heat, start to melt these objects. They begin to differentiate metallic cores, silicate mantles. You have aqueous alteration, forming clay minerals and hydroxides. You have thermal alteration, causing new metamorphic materials. You have shock minerals, impacts when two objects come together at hypervelocities. And these lead to roughly 250 minerals. They're new carbonates, but about 250 minerals in all at this stage. These are the building blocks of all the planets and moons, these 250 mineral species. We've gone from 12 to 60 to 250 just by processing. And the idea of mineral evolution is that you do process elements through fluid rock interactions by new ranges of temperature, pressure, ultimately through biology, as we'll see. A fascinating aspect of this is all of the chemical diversity that we see on Earth today was present. All of the rare elements, cesium and uranium, tantalum and beryllium were present, but there are no minerals yet. Those elements are somewhere. When you hold a chondrite in your hand, all those elements are present, but they're so widely dispersed you simply cannot find them. And so this is a mystery. Where is the beryllium? Where is the uranium when you hold that chondrite in your hand? It takes many years, billions of years probably of processing to get those minerals. Now, stage 3, Earth is formed. We start beginning to have processes, internal heat causing volcanism, causing igneous processes, metamorphic processes, standard things that are known in a volatile-rich body. This gets you up to about 420 different minerals, of which 30 are carbon minerals, graphite, diamond, moissanite, the carbides, a bunch of carbonates, roughly 30 in all of the carbonate minerals. There's a complete list, which I've just had accepted for publication, of about 420 minerals. If you're interested in knowing what minerals would be available to you for the origin of life, for example, that's where to find them. At least that's our preliminary list. And then when you form a planet like Earth, in fact, all the planets, the terrestrial planets, the outer layer is a basalt, a black iron, magnesium, silicate rock, which is very common on Mars. It's the mineral that you find on the surface of Venus and Mercury as well. Earth has enough internal heat, though, that you can partially melt that basalt veneer. And when you partially melt basalt, the liquid that results through 15 or 20% partial melting does not have the same composition. It's much more rich in silica, in alkalis, in aluminum, and so you form a mineral, a rock type called granite. Granite selects and concentrates many elements that were very rare before. It gets higher and higher concentrations of boron and beryllium and so forth. And so very quickly you get up to 1,000 minerals because you start forming various new minerals. Here are a couple of carbonates, a lithium carbonate, a beryllium carbonate, that would not have formed before granites and probably don't occur at all on Mars. This gets you up to 1,000 species, and then plate tectonics. And if you want to talk about ways of reworking huge volumes of the crust and upper mantle, you take a tectonic plate, a slab of lithosphere, the crust and upper mantle. It plunges down hotter and hotter it gets. It partially melts, and the melt arise, and those fluids interact through literally millions of cubic kilometers of Earth's upper mantle and crust, selecting and concentrating elements, forming all sorts of new ore deposits, new kinds of volcanism, various sorts of mineral-forming events, and so you get lots of new minerals. Here's a couple of carbonates that wouldn't have occurred before. This roughly gets you to 1,500 different mineral species. These new processes, all physical and chemical processes, processes that we think are deterministic on any planet that looks the size and composition of Earth, anywhere in the cosmos, that these roughly 1,500 minerals would arise by these processes. But then you're stuck. Try as we can. There are no physical or chemical processes that can take us beyond 1,500 minerals on an Earth-like planet. Yet today we have almost 5,000 minerals. What's different? Earth is alive. So we come to stage 6. This is this period of chemolithoautotrophs, before photosynthesis now, where microbes were not producing any new minerals at all, but rather they were taking the chemical energy available by the disequilibrium of rocks coming from the deep interior that were more reduced, interacting with fluids near the surface, which were more oxidized. That chemical energy released by redox reactions drives microbial communities. And so you have new kinds of deposits, a redistribution of rocks, but no new minerals. It was photosynthesis producing oxygen that was the game changer. This was the punctuation event in the evolution of minerals on Earth, and you suddenly have the potential to triple the number of mineral phases simply by producing oxygen. More than 3,000 new oxides and hydroxides. Virtually all of the copper oxide minerals, 369 out of about 400 minerals, are produced then. Uranium minerals, manganese minerals, nickel minerals, iron minerals, cobalt, molybdenum, you just go down the list. Thousands of minerals that would not have occurred before. Indeed, this is the single most important factor in the diversification of minerals on Earth. And more than 200 carbonate minerals. Carbon minerals occur for the first time, so 2/3 of all the carbon minerals appear at or around this time. Then we come to the most recent stage 10, Earth, the terrestrial biosphere. Now, I've skipped over some stages, but I want to emphasize that Earth has gone through at least 10 major transformations through its history, through its 4.5 billion years. It has looked different. It's chemically different, geochemically different, mineralogically different. 10 stages. I keep hearing people talk about Earth-like planets, but which Earth-like planet are you talking about? Maybe this is what you think of as an Earth-like planet. But Earth has only been this kind of planet for 8% of its history. And indeed, I wonder whether, as Lynn alluded to, is this not possibly the most extreme environment in our planet's history? Because the extreme redox potential that has been set up between the crust, which even a few meters down is something around 10 to the minus 70th log FO2, to the surface, which has free oxygen, is by far the most extreme gradient in chemistry that has ever existed in the history of our planet. It's sustained by life. Therefore, life is creating this incredibly chemically dynamic but very dangerous environment. Biomineralization occurs, new organic minerals occur. We have amazing nanotechnology. Individual lenses of these trilobite eyes are single crystals of calcite with the c-axis pointing out, but not just pure calcite. They are zoned from the center to the outside in magnesium and calcium to correct for chromatic aberration. Astonishing extreme mineralogy that is produced by life. So my conclusions: carbon has played an incredibly central role in cosmic mineralogy since that first mineralogy. The Great Oxidation Event is clearly the punctuation event that diversified the planet. It's the result of life. The biosphere plays many roles in the changing chemistry of the exosphere. We see this, by the way, this is absolutely just accepted work, and I'd love to talk to you more about it if you want to hear about it. But if you look through the past 3.5 billion years, modern going back 3 billion years or more, one sees that the mineral distribution of mercury, molybdenum, boron, beryllium, zirconium, that you see punctuation through this. You see pulses that are associated with the supercontinent cycle. There are details here that are associated with changing ocean and atmospheric chemistry, and astonishing changes in the very recent 500 million years that are associated with the rise of a terrestrial biosphere. All of these things that are revealed through studies of minerals through time. So, I want to end with these 4 questions, because this is, to me, the most exciting part of this talk. It's not what I can tell you that we know, it's all the things we don't know and what we're going to discover in the next several years. So thanks to the Deep Carbon Observatory, we have the opportunity to do this. And now, I thank you and welcome your questions.